Welcome tech enthusiasts to How It's Made, the go-to channel for uncovering the secrets behind the creation of everyday wonders. Today, we're delving into the heart of modern technology, exploring the mesmerizing journey of how microchips are brought to life. If you're ready to witness the magic behind the gadgets we can't live without, you're in for a treat. Let's dive into today's episode, How Microchips Are Made. Few things in the world are as basic as sand, and very few are as intricate as microchips. However, it seems almost impossible how silicon and sand can be turned into microscopic devices with millions of parts. So how exactly are microchips manufactured, and why does the process take an astounding 12 hours? Are you excited to find it all out? Here it is. Microchips are manufactured from silicon in multi-billion-dollar fabrication plants called fabs, even with the most advanced and costly technologies known to man. Why? Because silicon has a semiconductor covering. It can act as an insulator in some circumstances and conduct electricity in others. Doping, or the addition of contaminants, is one way to do this. This gives us the ability to regulate the flow of electrical impulses in addition to satisfying the requirements of various electronic devices. In addition, a lot of silicon is found in nature, which greatly reduces costs. Sadly, the majority of silicon found in nature is chemically bonded to oxygen, necessitating the separation of the two elements. Carbon monoxide and 99.9% pure silicon are produced by melting sand and carbon dioxide in crucibles. Ultra-pure silicon is obtained following additional processing. The next steps involves contacting molten silicon with a seed crystal. A single pure silicon crystal is created as silicon atoms adhere to the seed's crystal surface and pull it away. Subsequently, the ingot is sliced into a thin, round wafer using a wafer slicer, a precision cutting device. A slice's thickness ranges from 0.01 to 0.025 inches. To remove any imperfections, the surface where integrated circuits are to be produced is polished. This and the next procedures are carried out in a clean room with filtered air to eliminate outside contaminants. A few equipment operators in the room are dressed in gloves, head and foot coverings, and lint-free clothing. Even the light sources are filtered since the certain microchip components are sensitive to specific light frequencies. After that, a coating of silicon dioxide is applied to the wafer surfaces to create an insulating base and stop any silicon oxidation that would lead to impurities. In order to create silicon dioxide, the wafer is heated to around 1,830 degrees Fahrenheit or 1,000 degrees Celsius and subjected to several atmospheres of pressure, which allows the silicon to react with oxygen and water vapor. Temperature and exposure time both affect the thickness of the silicon dioxide coating. The circuit design is created using a computer-aided drafting machine onto the silicon wafer's surface. After that, the image is transformed into a mask. These photolithography masks serve as stencils for the designs and structures that will be transferred onto the silicon wafer since they are opaque in some places and clear in others. Here's an interesting process. Are you ready? A drop of photoresist material is deposited in the silicon wafer center during the photolithography process, and the wafer is quickly spun to spread the material throughout the whole surface. After that, the photoresist is baked to get rid of the solvent. The most crucial phase of the procedure is the following one, which is when everything comes together. The wafer is placed inside the photolithography apparatus, where it is exposed to ultraviolet light via a lens and mask that focus the light onto the tiny microchip area. The underlying photoresist on the wafer is exposed anywhere the UV light gets through the clear areas of the mask. The photoresist undergoes a chemical transformation as a result of this exposure, hardening. This process embeds the circuitry pattern that was originally on the mask into the wafer. Due to the extremely large gaps between circuits and components, ultraviolet light with a very short wavelength is used to pass through the mask's tiny, clear sections. Occasionally, the photoresist is additionally exposed to X-ray or electron beams. The wafer goes through a chemical etching procedure after being exposed to light. This leaves a three-dimensional microchip behind by removing the parts that were not exposed to the UV radiation. Certain regions of silicon must be doped with impurities to change its electrical characteristics in order to produce transistors and other electrical components. Ion implantation or diffusion are the methods used to add dopants, such as phosphorus or boron. The conductive and insulating areas of the microchip are defined in this step. Chemical vapor deposition, or CVD, and physical vapor deposition, or PVD, are two methods used to deposit different materials, including insulators and metals, onto the wafer's surface. These deposited layers are what create the insulating layers and conducting pathways that make up the chip's circuitry. A sequence of lithography and etching procedures is repeated to build up many layers of circuits. A chip's design becomes more intricate with each iteration. Microchips contain a basic set of components since they're essentially very small circuits constructed on a large scale. Transistors may either amplify or switch the electrical impulses that are going through. Resistors assist in controlling the electrical current, and capacitors can momentarily store an electrical charge. More than 28 billion transistors can be found in more sophisticated processors, such as those found in expensive graphics cards. The computing power increases with the number of transistors. The wafer is tested following the fabrication process in order to detect and remove any problematic chips. This is an essential quality control procedure to guarantee the finished product's operation. Following verification, each chip on the wafer is detached and put into protective packaging. In addition to offering electrical connections, these containers shield the chip from the elements. To make sure the packed chips fulfill the required performance standards, they go through one last round of testing. Functional, electrical, and occasionally environmental tests are part of this testing. Even with the use of precision equipment and a controlled environment, a large percentage of integrated circuit chips are rejected. While the percentage of rejected chips has decreased over time, it's still challenging to create an interwoven lattice of tiny circuits and parts, and some rejects will always occur. If significant process in electronic device technology is to occur in the future, it might entail the development of a completely new circuit technology. It has long been recognized that more advanced gadgets are achievable than the fastest microprocessors. For example, the human brain processes information far more efficiently than any computer, and some futurists have predicted that biological, rather than mineral processing circuits will be used in the next generation of processors. And there you have it. We've peeled back the layers of complexity to reveal the art and precision that go into crafting the microchips powering our world. If you enjoyed this deep dive into technology, don't forget to hit that like button, subscribe for more intriguing content, and share your thoughts in the comments below. For your regular fix of fascinating manufacturing processes, stay tuned to How It's Made. Thanks for joining us today, and until next time, keep that curiosity burning.